Okay, this is Unit 4 Bonding, and this is Lesson 3. And today we're going to start to talk about how we can write and name chemical formulas. So naming and writing chemical formulas. Each element within a compound has its own charge. We call these charges oxidation numbers. When you add them all up within a compound, they will equal 0. So all compounds are neutral. Oxidation numbers can always be found on your periodic table. You know where they are. They're in the upper left. Those are the positive and negative numbers in the upper right hand of the chemical symbol box. Remember, if it's a positive number, it means that it's willing to lose 4 or 2 electrons, and if it's a negative number, it means it's willing to gain 4 electrons. So depending on this, in this case, what carbon is bonding with, it might either lose or gain electrons. Oxidation numbers exist because different atoms can take on different charges in different compounds, depending on what elements you're bonding with and the number of electrons those elements want to either donate or accept. And I use the terminology in class, give up, meaning donate, give up, or take, accept. So in this case, you can see sodium has a +1. Remember, its electron configuration is 281, and it wants to give up that last electron right here so that it has 8 in its valence shell. Fluorine, on the other hand, is 27. It wants to gain 1 so that it will have 8. So what happens is fluorine takes the electron from sodium, and they combine at a 1-to-1 ratio. So NaF. If I were to draw this as a Lewis structure, I would have Na plus because it gave up 1, and then in brackets I would have F with its 7 valence electrons and then the 1 it got from sodium, and it has a negative charge. This negative is attracted to this positive and NaF forms. Now, unfortunately, there's some special rules for assigning oxidation numbers. Pretty much most of them are common sense, but there are a few exceptions to the rules that you will have to memorize. So uncombined elements, meaning those elements that are not bonded to any other type of element, have an oxidation number of 0. We sometimes also call this elements in the free state. This includes any formula that has only one chemical symbol, but it also includes Brinkelhoff. So anytime I have for example, Br2, it's going to get assigned a 0 oxidation state, F2H2. So let's look at some examples. If I have NaF, which we did, Na's got a +1 charge. I can find that in the upper right box, and F has a -1 charge. That's what we do when we assign oxidation states. If I have CaCl2, Ca has a +2 charge. Now, chlorine has a -1 charge. And you might say to yourself, well, how is this neutral then? A +1 and a -1 is a +1. However, you have to look here. There's 2 chlorines. So really, if each chlorine is -1, then the whole charge of the chlorine is -2, and a -2 and a +2 is 0. And I'll show you how to do that a little bit later on in this lesson. In compounds, remember they are neutral and have two or more different elements bonded together. The sum of the charges must add up to 0, and that's what I was just telling you. So the ions within a compound have oxidation numbers equal to their oxidation number found on the periodic table, and that's what I just did here. So let's look at a couple examples. Na is +1, and I only have 1. So 1 times +1 is +1. Cl has a -1 charge. I'm getting this from the periodic table. There's only 1 here. So 1 times -1 is -1, and that equals 0. Over here, Mg is +2. There's 3 of them in this compound, so 3 times +2 is +6. And N has a -3 charge, and there's 2 of them. So 2 times -3 is -6, and that equals 0. Now, you don't have to write it below it like I did here. I'm just showing you. I do the mental math in my head. +2 times this 3 is a +6, and a -3 times a 2 is a -6, so that equals 0. Here's an example. When you have something with 3 elements, always assign oxidation numbers to the elements that only have 1 charge. So for example, when you look at oxygen on the periodic table, it only says -2. So -2 times 3, that's a -6 there. I'm just going to write that below it. Hydrogen has a +1 charge, and there's only 1 of them, so that's +1. So if the whole thing has to equal 0, and I have a -6 and a +1, then nitrogen must be +5. Now when you look at nitrogen, it's got a whole lot of charges. It could be -2, +3, -3. Okay, so you have to figure out the charge of the nitrogen mathematically. Okay, you can't just go to the chart and pick the one you see. We assign oxidation numbers to the elements that only have 1 charge, like oxygen and hydrogen, and then we figure out the third one mathematically so that the net charge on the compound is going to be equal to 0. The oxidation number is the number inside the parentheses. It is the charge on just one of that element. So when we were looking up here at the other example that I did, what was it, MgCl2. So we had Mg was +2, so we had 1 times +2. That's this charge right here. And then we had 2 times -1. So that was the charge. That's what they're talking about right here. Remember that we always write the positive element first and the negative element last in a compound. This is extremely important. So when we look at MgCl2, this is positive, we write it first. The MgCl is negative, we write it second. So let's look at an example. H is +1, Cl is -1. H2O, H is +1, O is -2. Positive, negative, positive, negative. The exception to this rule is ammonia. This is ammonia, NH3. It's like the stuff that you use to clean your floors. The N is -3 and the H is +1. Okay. We've already mentioned this before in the periodic table. We know that all group 1 metals, which are our alkali metals, all have an oxidation number of +1. If you looked at all of them in group 1 from top to bottom, +1. Our group 2, which are our alkaline earth, all have a charge of +2. Example, Na is +1, Cl -1. Ca is +2, Cl is -1. Fluorine is always a -1 in compounds. The other halogens, Cl and Br, are also a -1, as long as they are the most electronegative element in the compound. So this is referring to table S when we talk about electronegativity here, most electronegative. So here Na is +1, F is -1, H is +1, Br is -1, Li is +1, Cl is -1. Hydrogen is going to be +1 in compounds unless it is combined with a metal and is at the end of the formula. Then it is next -1. So what this is called is, here this is +1 -1, but here this is called lithium hydride, and it's called a metal hydride, and that's because lithium is a metal. So I could replace this lithium with anything else. When you form a metal hydride, hydrogen is going to be -1, and the metal will keep its regular charge. So what that means is that lithium will give up 1 and hydrogen will gain 1. Oxygen is usually -2 in compounds. Here H is +1, oxygen is -2. +1 times 2 is +2, and a -2, the net is 0. Here carbon is +4, oxygen is -2. So I have a +4, -2 times 2 is -4, the net charge is 0. Okay, these up top are your oxidation numbers. That's what I'm interested in when we write things out. This down here is the net charge. If you want to put it there, it's fine. I'm not looking at it. I do it mentally in my head, but when I teach you, I do it out so that you can see where it's coming from. When combined with fluorine, which is more electronegative, oxygen is +2. So this is one of the exceptions where oxygen will not be -2. It's when it combines with fluorine. Fluorine is -1, oxygen is +2. This is -2, +2. The other exception is when a peroxide is formed. Oxygen is going to be -1. A peroxide is a compound that has the formula X2O2. This X is interchangeable, so it could represent a variety of elements. So it'll be some element 2O2. So here, this is hydrogen peroxide. This is what we put on our cuts. Hydrogen is +1. That gives me a +2. This is a -1, -2. It equals 0. And this is sodium peroxide. So oxygen will always be -2 unless it combines with fluorine, in which case it's a +2, or when it forms a peroxide, in which case it's a -1. The sum of the oxidation numbers in a polyatomic ion must equal the charge on the ion. So you go to table E and you find chromate, and you'll see that it has a -2 charge. Since this is an ion, when we do the net charge, it's not going to equal 0, it will equal -2. So if I look up oxygen, oxygen's -2 times 7 is -14. If I look up chromium, chromium is +6. Sorry. That's going to give me a +12. A plus 12 and a negative 14 is a negative 2. So whenever you have a polyatomic ion, the net charge equals the charge on the ion. Compounds containing polyatomic ions, as we've already said, have both ionic and covalent bonds. So I want you to list the polyatomic ions in the following compounds. The first one we will do together as an example. So here I have NH4, which is ammonium, and I have 3 of them. So I have 3 NH4 plus. And I have a phosphate, which is going to be PO4 3 minus. So I want you to pause me. I want you to try to do the rest, and then I want you to check your work. You're using table E to do this. Okay, so you're back checking your work. In the next one, the polyatomic ion could be 2 different things. I could either go with CO3 2 minus, or I could have gone with HCO3, which is hydrogen carbonate, and that just has a minus sign. In the next one I have 2 polyatomics. I have the ammonium ion again, and I have the nitrate ion. In the next one I have 2 possibilities again. I have SO4 3 minus, and that's probably all you put. That's fine. There is another one, but it's not listed on this chart. It could be HSO4 minus. In the next one we only have 1, and that's the nitrate ion. Okay, let's do a few review examples here. Oxygen is always -2, except in peroxides. Therefore, H must have a charge of, so if this is -2, and it has to add up to -1, then H must be +1, because -2 and +1 is -1. Must add up to -1. That's the charge on the OH ion. PO4. So it's got to add up to -3. Oxygen has a charge of -2. So that's -2 times 4, which is -8. If this has to equal -3 and this is -8, then phosphorus has to be +5, because +5 and -8 is -3. And you would see, you'd go to phosphorus and you would see, is that one of the charges on the table? And it certainly is. Okay, that's all, folks. See you tomorrow.